Hello everyone, my name is Boinde and my research is on rapid compact optical shutter using DC model and 3D modeling to bring affordability and reliability to precision spectroscopy. What is an optical shutter? An optical shutter is basically a device that opens and closes to allow radiations to move through an aperture. And with regards to this, shutters are becoming or are very prominent in laser-based experiments, and they come in diverse features, shapes, and operation mechanisms. And an example is the acousto-optical modulator, otherwise known as AOM, which uses sound to basically act like a shutter. Another example is the laser safety shutter. We have the electric fast shutter. And so operations of shutter are very common in precision spectroscopy, which are basically precision experiments involving electromagnetic radiations, where we need to provide a fluorescence to an ion, and we need shutters to help us achieve that. Now, despite the availability of different designs of shutters, a shutter is deemed favorable with regards to the required features that a lab needs. And this could be the size of the shutter, the light extinction ability, that's the ability of the shutter to completely block out light, and the speed at which the shutter does that, and the ease at which the shutter can be set up. And also the price also plays an important role. And so numerous labs have resorted to customizable designs of shutters. And this is actually the motivation for my experiment, where I design, print out, assemble, and troubleshoot a shutter driver and body to directly replace the old shutter system of the Iron Lab in the CUA of MIT. And I need features such as long lifespan, 1 millisecond activation delayed at the time to activate the shutter motion after a signal is sent, approximately 1.5 milliseconds switching time. That's the actual time it takes for the aperture to open or close. And the shutter needs to have no observable jitter. That's the errors in periodic motion of the blade. And to accomplish this, I comprehended the existing driver design. That's when I say driver, I mean the circuit that moves the motor. Then assemble the components and build the driver, build circuits to assist driving and testing process, troubleshoot and replace the components as needed. 3D design and print shutter body and blade and complete shutter assembly, and then test it using a scope, and also test it in an experimental situation that's involving the fluorescence of an ion, and optimize my design afterwards. So in my findings, I was able to find out that the operation of the current through the motor is periodic with signal change, and it provides a kick for the blade's directional change. And this is seen in the trace in the upper right corner right here, where we have a TTL signal change from high to low, and that is followed by a kick in the current, and it also occurs in the opposite direction for the blade to switch in an accelerated manner. And this brings us to the trace for the activation delay, where we had an activation delay of approximately 2 milliseconds and a switching time of 400 microseconds. And this was done for two aperture sizes, a 0.1 and a 0.15 opening. And then we discovered that, or I discovered that there's no significant change in activation delay and switching time for aperture changes of these two. And in the context of the experiment, where we shined lasers through an iron, and we operated two shutters, an AOM and the shutter I built in this sequence in order to provide an efflorescence within this range. And we can see that there will be an activation delay in the shutter time, because AOM has a property that it works really fast, and that delay is corresponded to the 3.5 milliseconds, and it's also a delay when you tell the shutter to close, and this averages to 2.8 milliseconds. And there was no observable jitter also in the behavior of my shutter. So based on the findings within the parameter of the experimental test of on ytterbium, the activation delay time was sufficient, 2.8 milliseconds, which is good enough for precision spectroscopy. And the switching time was well below 1 milliseconds, which is way more than what we expected. And from video evidence, the motion of the blade experienced no observable jitter. So all in all, this is good, but then we do know that the activation delay limits the ability of a shutter to work with narrower pulses. And in a long run, we will need to find a way to reduce the activation delay below 1 millisecond. And to do that, we need to use our results and understanding of the current through the model to do further research on the DC model response time in order to get down its activation delay. And this brings me to the end of my presentation. And these are my references. Thank you very much.